Welcome and hello. This is a video exercise in HEC HMS, and in this exercise, we are going to be dealing with exponential loss, calibration, and optimization. In this video, we will build a simple model from scratch, generate our own precipitation data and observed discharge data, run the model using the exponential loss method, and then calibrate the loss method parameters, first manually and then using an optimization trial. All right, so that's the direction we're going. What I have on the screen here is DSS view. We'll actually get to that pretty quick. Here is my HMS. I'm running version 4.12, but this exercise should work in any version. I'm going to start by creating a project. So file, new, exercise 52. You can call your project whatever you want and put it wherever you want. So click on that folder icon and find a place on your computer you want to save that project directory. Okay, I'll put it right here. And then for units, I'm going to use US customary units and then click create. All right, let's get started here. I'm going to just start simple. It's going to be a very basic basin model. So I'll just create the basin like that and then click on the basin one to show the basin. And I'm going to place a sub basin. I'll call it sub basin one. And boom, we're done with the network. This is all I'm going to do for building a hydrologic network. The focus of this exercise is not on building the hydrologic network. I'll go ahead and click on that subbasin and show the properties. We're going to return to these properties a little bit later, but what I want to do first is build the precipitation and discharge time series data sets. I can actually do that in HMS first and then generate the data in just a moment. So let's go up to Components, Time Series Data Manager. The first will be a precipitation gauge, so new. I'll just call it precip gauge. It's fine. And then create. Okay. The other gauge I want to create is a discharge gauge. So I'll just call it discharge gauge. All right. And create. All right. So inside my time series data directory, I've got those two gauges I just created. Now I want to be using a DSS data set. I don't want to do a manual entry on these. So let's go ahead and generate that precipitation data and discharge gauge data. I've created an Excel file here, which is what I'm calling a precipitation generator. And what it is it's just an equation here. You can use this equation if you want or whatever. Very straightforward and simple. The very first hour of a 10-day simulation starting on January 1st, 2020 is going to be 0 inches of precipitation. And then the next hour is going to have an equation based on the previous hour and some random variables. All right, so that's how I'm generating the hyetograph you see in this plot right here. I can just regenerate the equations to create a new hyetograph is what I'm doing. So let me go ahead and regenerate a few hyetographs to kind of show you how I got started doing this. Here is the sum of the precipitation. It's 2.75 if I looked at all the numbers down here and summed them up. And then the maximum precipitation is 0.16. Now that's just for the values here in column 8, which is the precipitation generator that was generated using this random function. All right, so 1 second here, I'm going to generate a few more. So here's a second storm. And then if you look at the graph, it should be changing. There's another one, and so on. I changed it so there will only be precipitation in the first 5 days of this 10-day simulation. So you may see an abrupt cutoff of precipitation at the halfway point, which might be what's happening here. This hyetograph has 4.63 inches of precipitation with a maximum of 0.18 inches per hour. So let me just do a few more. So what I was looking for is a storm that would generate between 5 and 10 inches. Like this is a pretty good storm here. This is 9.3 inches over the first 5 days. A few different Excel options that I used on this Excel file, which you may want to do yourself, is first of all, change the columns to numbers. I just hard to add letters personally. And then I'll show you how to do that. The other one involves the automatic formula generation. So if you go to File Options and then click on the Formula menu on the left, R1C1 reference style is what I like to use. And then also under workbook calculations, I just click on manual. So if you want to regenerate the equations to give yourself a new hyetograph, then you just click F9 once you're on that worksheet. So I have some hidden columns here, which represent the values that I want to use. So let me unhide them. These are the values for precipitation that I want to use, and then these are the values for discharge. I got these precipitation values using the generator, and then the discharge values I figured out using HMS, running the model and kind of working backwards. All right, so let's go ahead and use these values for my time series data set for precipitation, and then these ones for discharge. Before that, we can go to DSS view and create a DSS file, which will serve as a container for our data sets. All right, here is my project. I'm going to put this DSS file in the data directory and just call it data and create. Okay, so that file has been created. Now I'm going to go up to data entry, manual time series. All right, so this is the form I want to fill out. For part C, I'm going to say precip INC. And then for part E, I want to make sure it says 1 hour right here. That's fine. I'm only going to have one precipitation time series data set, so I don't need to be any more precise or unique with parts. All right, so for the start date, this is going to be on January 2020. I'm going to start at 0 o'clock, and the units will be in inches. And then the type here, this is also important. You want to use period cumulative. All right, that looks good. Now back to Excel, I'm going to highlight all the records in that precipitation column. So that's going to be hourly data for a 10-day time period. I'm going to click on that first record and then click paste and then save. Okay, I don't need to return to the data screen, but I do want to take a look at this data. So this is the plot right here. If I zoom in, I can confirm that it takes on the same type of a hydograph shape, like a bar graph shape right here. Maybe I'm too far zoomed in. Now I want to do the same thing for the discharge gauge. So I'm going to go up to data entry, manual time series. For part C, I'm going to say flow. It's also going to be 1 hour for part E. All right, so same start date and time. The units are going to be in CFS, and then the type is going to be period average. All right, now all I need to do is paste in those numbers. So back to Excel. Now I'm going to highlight the discharge values, Control C to copy, and then come over here. I think I can just go Control V. Okay, looks like that worked. Let me go ahead and save it and then preview the data. So here is the flow, and then here is the observed discharge for that subbasin. So I'm going to go ahead and make these assignments in HMS now. Back to HMS, I'll click on the precipitation gauge. I'm already there. For the data source, I'm going to select DSS and then file name. I'm going to navigate to that DSS file. Here's the project. Here is the data directory. Here's the DSS file. Select. And then I need to also assign the path. So that's right here. This is going to be the precipitation and then set path name. And then when I click save, it should update the units to inches and then the time interval to 1 hour. Let's see. Okay, that looks good. Now let's do the same thing with the discharge gauge, the observed flow. So I'll select DSS, and then for file name, here's my project data, data directory, data.dss. Okay, and then now this is going to be the discharge or the flow and set path name. All right, so it should change to CFS in 1 hour. That looks good. We're now ready to make some more edits to our subbasin. So all we've really done so far is create the subbasin. And if I click on the subbasin here in the basin model, the component editor data shows up down here where it's got a number of tabs. The main tab is this subbasin tab. So this is where we're going to start. And then it also has an options tab, but then the intermediate tabs like loss, transform, and base flow, those refer to selected methods down here. So the first edit I'm going to make is Clark unit hydrograph. This is the transform method I want to use for this exercise. And then I'm going to click on the transform tab. And then for time of concentration and storage coefficient, I'm just going to use 5 hours and then leave it at the standard method. Back to the subbasin tab here. For this loss method, I want to change this to exponential right there. And then I'll go to the loss tab. And now we need to put in some parameter data associated with that exponential loss function for infiltration. And the starting values I'm going to use here is going to be 0, 0.1, 0.8, and 0.8 for the initial coefficient, coefficient ratio, and exponent. I'm going to leave the initial value 0 and percent impervious as 0. But what I'm going to do over the course of this exercise and the calibration and optimization is to change these 3 variables so that the discharge that's computed through HMS will hopefully match that observed discharge that we just inputted into DSS view and into our discharge gauge. But these are going to be the initial values that we use for our first simulation run. Before we leave the subbasin, I wanted to eliminate base flow. I know that's fairly unrealistic, but the focus of this exercise is to do the calibration and look at the parameter values for the exponential loss method. So just keeping things simple, no base flow method, and click save. All right, next what we want to do is go and add a meteorologic model. So we'll go Components, Meteorologic Model Manager, New. I'll click Create. Okay, so up here in the Watershed Explorer, I'll click on MET1. And then the default is what I want to use here with the specified hyetograph as being my method of precipitation. I also want to change this replace missing to set to default. All right, and then so the only thing we really have to do here in the MET model is specify that hyetograph, which is what we generated with that precipitation gauge. So in the Watershed Explorer, click on Specified Hyetograph, and I need to first associate this MET model with the basin. So click on the Basins tab here. So click on MET Model 1, Basins tab, and then change this Include Subbasins from No to Yes. That way, Subbasin 1 here should appear as a subbasin to select our precipitation gauge for. And there it is. So specified hyetograph, and now I should have my precip gauge right there, and save. Another thing we need to do in this model is create a control specification. So I'll go up to Components, Controlled Specification Manager, New. I'll just call it Control 1. That's fine, accept the default name. It will be our only controlled specification. And we need to specify that date time again. This is going to be the duration of the simulation, 0 o'clock, and then the time interval is going to be 1 hour. One last thing we need to do is assign the observed flow discharge to our subbasin. So I'm going to click subbasin once again, and then click on this Options tab. For observed flow, I should be able to select, yep, there it is, discharge gauge, and that looks good. Click Save. All right, let's go ahead and create a simulation and then run it and check out our results. I'm going to go up to Compute, Simulation Run Manager, New. Well, we'll call it Run 1. That's fine. It's the only one we're going to use. The basin model, it's our only basin model, our only MET model, our only control specification. So that's pretty straightforward there. Click Save. Up in the Compute menu, we can now select our simulation run right here. If you don't see this Compute menu toolbar, you can go up to View, Toolbars, and then click on Compute. And I'm going to toggle off 2D. Okay. So that's that. You can just toggle that on and off by clicking it. Another way to run the compute is just to come up to here, right click, and compute. In fact, let's do it that way, or you can click this button, but I'm going to give that a shot. Okay, I forgot something. No area is set for the subbasin. That's right. So what I want to do is just set it to 10 square miles. That is another required field, which is right here, and I forgot to do that. Okay, save and compute. All right, looks like it ran. That's good. I'm going to click on this subbasin, right click, and then graph. What we have here is the hyetograph on top and then the hydrograph of discharge on the bottom. This bottom plot is what we're really looking at in terms of calibrating our parameters. So if I zoom in, you can see that we already have a very strong correlation between the computed and the observed data, where the computed is in blue and that the observed data is in black. So it has a similar pattern, you can see. I'm just looking at the peaks here. I could zoom down as well. But what we need to do is make a little bit of a modification. Before we do that, let's also look at the summary table, which shows us a NASA cliff score of 0.982, which is very strong, arguably good enough, as well as a percent bias of 12.73%. So we're a little bit over the target value. Next up, I want to make a few changes to the 3 variables I mentioned earlier. These will be our decision variables, and they're associated with that exponential loss infiltration method. The initial coefficient right here, this specifies the starting loss rate coefficient on the exponential infiltration curve. In our first trial run using these numbers, there was too much discharge, which means we need to increase the loss, increase that infiltration. So what I'm going to do is just for our second trial, change this value from 0.1 to 0.2. And even though I'm considering these other 2 variables, decision variables, I'm going to leave them alone for this second trial and then just rerun the simulation by making that one change. And then let's go ahead and see how that affects our results. Okay, so that ran again. And then let's take a look at the summary table, or the graph first. And this looks like we actually underestimated a little bit. So if I zoom in here, we see that the computed value in blue is now below the observed value in black. And then if I look at the summary table, we have better results than last time. Nash Sutcliffe is up to 0.991. And now you can see the percent bias is negative 0.787%. So we're a little bit under our target, but we're still very, very strong. In real world situations, this would probably be good enough, but I've already set up this exercise so that we should be able to attain perfect values. So I'm going to close that dialog box, come back here to our parameter values. Now I'm going to leave 0.2 as it is and then change the coefficient ratio for this third trial. The coefficient ratio indicates the rate of the exponential decrease. And this refers to the rate of loss. So if we want more runoff, we want less loss. Therefore, we want to increase this coefficient ratio. Now, I don't have really a strong sense of how much to change it by, but manually I'm going to do a 1.2. So I'm changing it from 0.8 up to 1.2. And then after this trial, we'll get to the optimization so we can get perfect results. But there we go. Let's go ahead and save that and then run the simulation once again. The graph should be very close, and it is. So I'm not even going to look at that too close. I'm going to look at the summary table. Here we have 0.994. We're still getting closer, but we're still under on the percent bias of negative 6.07%. All right, it's time to stop messing around with the manual edits. Let's go ahead and create an optimization trial. So we'll go up to Compute, Optimization Trial Manager, New. I'll just call Optimization 1, Basin 1, and Met Model 1. All right, let's go ahead and make some edits to that optimization trial. So in the Compute tab right here, I'm expanding my optimization trials. And then here is some of the data I already input. I need to specify the time range, which is similar to the control specification. Well, I'm just going to put in the same data as the control specification here. It's going to be a 1 hour time step, so that looks good. And then let's see, for the search tab, I'm going to use all the values that are already here. These are pretty good. Default values for what I'm using, simplex, 100, 0.01, and absolute tolerance. And then with the objective tab, I want to minimize the discharge out of subbasin 1 using root mean squared error and minimizing. So all these values are exactly what I want them to be. I need to put in the same start and end date time though, and 0, 100 hours. That's one of the benefits of having such a simple basin model is there's not a whole lot of parameters to choose from here. All right, now I need to put in my parameter data. As I mentioned before, I have 3 parameters. So to do that, I'm going to right click and then add parameter. I'm just going to add 3 parameters right now and then make the edits in just a moment. Okay, parameter 1 is going to be that initial coefficient. So for element, I'll select subbasin 1 for all 3. And then for exponential, this is that initial coefficient. Okay, so the initial value will be 0.2. And now I need to set a maximum and minimum range, which would be, I'm going to go from 0 up to 0.3. All right, and then parameter 2 is going to be, again, subbasin 1. The parameter value is going to be the coefficient ratio right here. The initial value of 1.2 is fine, but then I need to set the minimum range to be 0.3 up to 2. So it's a much smaller range than the default to help the search find an optimal value. And then for this third parameter, subbasin 1, we're going to choose the exponent. So all 3 of these parameters are associated with that exponential loss. The initial value will be 0.8. The minimum value, I'm going to say 0.3. And then the maximum value I'll say is 0.99. All right, so click Save. We're ready to run the optimization now, so make sure you have Optimization Trial selected here in the Compute dropdown, and then run the compute. Wait for the iterations to cycle through. I set it to a maximum of 100 iterations, and it looks like it converged at about 69 there. Now let's take a look at the results. If I click on the Results tab and expand Optimization, I can see, let's look at the optimized parameter values. So here we started with 0.2, 1.2, and 0.8, and then we have converged optimal values of 0.11, 0.87, and 0.64. So it wasn't too far off from what we started with, which is not surprising because our simulation runs were actually very accurate. You're welcome to go ahead and look at any of the other tables or plots here in the optimization trial results. but I'm going to go ahead and do one final simulation run using these optimized parameter values, and then just take a look at the observed results and confirm that they are perfect or optimal. I'm going to click on the subbasin once again, then click on the loss tab here. And I've recorded these numbers down to the 10,000th. So I'm going to type in 1198. For the coefficient ratio, it was 0.8787. And then finally for the exponent, it was 0.6493. All right, so I'm going to go ahead and save that, select simulation run, and then run it. And that is run. Okay, here is the plot. And I really can't tell the difference now between the blue computed value hydrograph and then the observed, which is in black. But here's the moment of truth. Let's take a look at the summary table. And voila, we have a perfect score for Nash-Sutcliffe as well as percent bias. It's a 0% bias and 1 on Nash-Sutcliffe. So that concludes this exercise using the exponential loss method within our HMS model. We generated the precipitation data and discharge observed data manually, and then ran a few simulations and ultimately ran that optimization trial to find out the optimal values for our parameters.